name is Jon, and um, today my topic is regarding how to derive information by using remote sensing to understand urban divide. So by referring to urban divide, I'm mainly talking about the socioeconomic status of the urban groups, and also potentially regarding their demographic status. And I think this is a very important piece of information for understanding how different people are exposed to different environmental variables, and also for risk management. So before jumping to the details, I think I'm also trying to show you a little bit more about my research background, so that we can know how we arrive at this topic. So basically, as Steph already said, that I'm trained as an urban remote sensing researcher, basically focusing on images. So I'm looking at images every day and trying to understand how cities are interact with the environment. I started to look at how the urban land specification interact with environmental variables, and also urban climatic variables by using remote sensing image back to the start of my PhD research, where I especially focusing on temperature mapping. So I use temperature or heat mapping as a study case to test meaning of the statistical modeling, try to build the relationship between land surface and the temperature. After that, I started my postdoc research in Netherlands, and plus 1 year as a visiting scientist at ITC, and where I also started to focus on something on the ground. So apart from the modeling of the atmospheric or climatic variables, I started to also trying to understand how different people are exposed to these different environmental variables. So basically, visually, my research is pretty much framed by this small scheme where two basic components of information are involved. One is the environmental or atmospheric variables. Try to do that, try to obtain this kind of information through statistical modeling. And the other one is try to derive information or knowledge regarding how different people are distributed over the city in terms of their socioeconomic status and demographic characteristics. And for today's talk, I think I'm going to focus on the information on the lower part, because I was just talking to Steph that I realized that so lately that last week Oscar was already giving a talk on temperature mapping. So today I think it makes sense for me to focus on the lower parts. So when we talk about the socioeconomic groups or demographic status, it's very important for us to know how divergent that people are interact or impacted by the environment, the climate, especially if you try to switch your view from this very synoptic view captured by the remote sensing images to the ground, to the story on the ground in terms of the living conditions, not only regarding the living conditions about their built forms or the housing conditions, but also regarding something that's not really physical, but regarding the accessibility to different resources in terms of water, energy, electricity, etc. So also about sanitation level. So if you're really thinking about the extremes, that's the information regarding different types of different built environment and living conditions on the ground is really a very important information to capture, and also to understand how they are, how the different capacity of the people living in this environment to adapt or to mitigate the exposure. So by saying this, here's another image showing that if you're really thinking to the extremes, thinking about the very poor group of people in the city, and this group of people are really, the number of these people are increasing tremendously for the next coming decades, as you can see. So in this talk, I think I'm going to walk you through the general idea how to derive this kind of information by using remote sensing. So it's a very overarching overview of this kind of practice. I'm going to start with the basic rationale, the assumptions that we make to derive such information. I'm also going to first focus on a very simple scenario where we try to detect the poor people out of the other type of neighborhoods. So it's basically a very simple scenario. So try to make a binary, differentiation. Starting from there, I'm also going to talk about the existing bottlenecks, limitations, and strength of using remote sensing in deriving this kind of information. Following that, I'm going to also show you what are the alternatives that people are trying to derive more interpretable knowledge about the socioeconomic status and the poor people. Before closing, I'm also going to show you some examples. As you can see that these are the very general, the flow that we can follow to the left-hand side of the slides. So the basic rationale or the assumption that we can be able to detect or differentiate socioeconomic status of people from the images like this, from the view from above, is that we're making a very fundamental assumption, which is that the socioeconomic status or the demographic characteristics can be manifested physically by the physical experience captured from the above. And as you can see, there are a few images showing the very extreme and very significant contrast between different social groups on the ground. So as you can see, the first image is showing the slums, the building configurations of the slums, in contrast to formerly built areas. I think it's in Mumbai, India. The other image on the upper right is an image from Nairobi showing the same information, the contrast between different social groups. This image over to the left, lower part of the left, is an image over Mexico City in Mexico. And lower right, again, another image of Mumbai, India. So that's a basic assumption that we made. So socioeconomic status and the physical and demographic characteristics can be manifested physically from the image. Otherwise, there's no reason for us to do this, right? So in the simplest case, how do we differentiate these patterns? In this regard, the problem reduces to the very simple scenario of binary image classification. So by looking at this image, of course, as human beings, it's very simple for us to differentiate in terms of these building patterns, also the patterns of the street network. But for computers, they say totally different images. So when you zoom in, this is what computer actually see. They only see the brightness of the pixels. So in order to allow the computer to make the differentiation between the patterns, we need to compute something over the pixels, so which we refer as pixel patterns or image features. And there are many tools to derive this kind of information, such as one of the most famous set of measurements is called the GLCM. It's very conventionally used in the remote sensing community, that people try to compute image features in terms of the relationship between the pixels. So for example, you can of course compute how the central pixel different from its neighborhoods along different directions, so that you can be able to extract information such as gradients. A gradient means there is a boundary, right? There's an edge, there's a change or contrast in the image. And you can build other statistics over the more simple image features, so that each of the pixel can be encoded as a part of edge, as a part of more homogeneous patch, or as next to another line, or as next to many other lines in different directions. So it depends on how you would like to be really complicated in deriving information regarding the image features. So as I said, so if you can compute, for example, a contrast or a gradient along the horizontal level, you can of course extract the patterns such as the vertical lines. And you can extract image features as horizontal lines. So these are roughly horizontal lines, the vertical, horizontal. And you can also compare to the image features extracted from a totally different urban environments captured by the remote sensing image. You can extract more. So by doing this, each of the pixels are encoded as I said, encoded as a part of the feature. So it's a part of line, it's a part of homogeneous patch, which means, for example, if you have two features computed over each of the pixel location, it means that the pixels can be projected into a feature space where you can make the classification. So that's a basic idea in a few minutes that I walk through that to tell you how people are using remote sensing image to make the differentiation. Of course, the classification can be either artificially or automatically. You can, of course, set up manually set up a threshold in the feature space to differentiate the pixels. And of course, you can also use few nicely labeled pixels to train a machine learning model and reapply the trained model to another places, to other images, so that the model can automatically make the classification. That's basically relating to the practices in machine learning community. So again, you try to project the classified pixel back into space, and you have a nicely classified binary image. So in this very simple scenario, just briefly recap the workflow in this kind of practice. So of course, there are many other very advanced version of this workflow, but basically the key components are, you of course need the data, you need your inputs, and then you need to capture some feature or more advanced statistics over the basic features, and then you make the classification either manually or automatically. So I can of course make show you some examples that we try to apply this kind of practice in our study case. This is an example we have done in nearly 3 years ago, that we try to detect the very small poor neighborhoods by using training samples in this yellow boundaries. So this yellow boundary, zoom in, you can see that these are actually the labeled poor neighborhoods, showing quite a contrasting spatial configuration in terms of the building arrangement. And we train the model by using these patches along with other example where, well, the poor neighborhoods are not present as negative labels. So we train the model and reapply the model, try to detect the similar neighborhoods around the city. As you can see, those neighborhoods are very small. I'm sorry that I make the figure too small. Many of the neighborhoods, large amount of the neighborhoods are below a few hundred square meters, but with very densely built areas occupied a lot of people. And so you can already imagine the living conditions in terms of this information, and try to reconnect to the images I showed you before. So how people are living on the ground. So from above, and you try to relate to the story on the ground. So I can, of course, generalize the workflow visually as I show in the text in a few minutes before. You start from the raw image, you try to extract the image features, and then you try to map out the desired pattern of the neighborhoods, which are implication of the socioeconomic status of the people on the ground. And of course, in the model, in the workflow, you need a model, you need a classification model. As I said, in this entire workflow, we of course encounter different challenges, problems. And one of the key problems is that we have problem with the input data. So the input data is the source of information that you can derive further information. So of course, if the information contained in the input is very rough, you don't expect to extract the features that representing really detailed patterns regarding buildings or streets. So as you can see, as at the resolution of an image equivalent to something like a Landsat image with 30 meters, you don't see anything regarding the building patterns. So that's the basic information that you can have. So in order to compute features in different neighborhoods, like I show you that you can draw a neighborhood around each pixel and derive image features, and the input quality, the input data information is of course going to influence the features that you extracted. We also conducted some research a few years before, so this is a small experiment, try to detect and try to inspect how the resolution will be influencing the separability in the pattern on the image. So as you can see that when you have a very high resolution image, the separability is not really optimal because when the resolution is very high, there are also potential unwanted variations, which increase the intra-class variance. So I will talk about it later on. So when the resolution is approaching a certain level and the separability is optimal, so that the pattern between the two images can be detected with in a more desirable situation. So along the workflow, as I said, you can make the workflow, of course, automatic by using smaller training samples to train a model and then to reapply the trained model to a larger area. So this is the model advancement. So it can be started with a very basic scenario that you have to set up manually about the classification threshold, and then you can switch over to more advanced machine learning based model to make this workflow automatic. And this kind of workflow is advancing very quickly, so that these days it's very likely for you to escape the extraction of the image features. For example, by applying deep learning models. Of course, deep learning model is also referred as the representation learning, which means that it tries to detect the pattern you want while learn the features automatically at the same time. So the basic rationale is that the deep learning is adopting an algorithm which is called the backpropagation to backpropagate the error into the network, and so that the weights can be adjusted in each layer of the deep learning. And at the end of the day, once the parameters is adjusted or fine-tuned, and it's kind of magically in each of the layer, the model will produce some meaningful features, image features that can be useful for you to extract the patterns. So that's basically the advancement of this workflow. So ultimately, we're in a situation that we could be able to jump directly from an image to a desired patterns. So in any kind of situation, in any kind of scenario, in mapping vegetation, in mapping soil or other kind of geographic or geological patterns. So by applying deep learning, for example, you can directly start with the images from different kind of sensors, and then you try to map the desirable patterns. But by looking at this kind of workflow, it's quite interesting to see that if you would like to build some more knowledge, further knowledge regarding the detected pattern, almost always you have to relate this detected pattern to some other indicators. So for example, in vegetation mapping, if you detected vegetations, the patches of classified vegetations, you would like to at least build some metrics. For example, in relating to the spatial distribution of the vegetation, you need to build some other model on top of the detected pattern, or you relate this detected pattern to some other environmental, geological, geographic patterns to interpret the detected patterns. So this is the basic rationale in this workflow. If you try to understand more scientifically, So we're in a situation that the capacity of remote sensing, of course, is highlighted in this part for detection. The strength of remote sensing is for detection. And for and this situation also applies to, of course, the situation that we're looking at. Try to detect the pattern of the poor neighborhoods of different socioeconomic groups. And once we have detected patterns, we also would like to know more about this pattern. So we try to relate this detected pattern to other indicators, socioeconomic indicators, incomes, health, whatever. You would like to explain this detected pattern. So in this sense, the scientific knowledge, I would say, is more or less derived from this part in this specific situation. And the remote sensing is more or less highlighted by its strength in detecting patterns. So if we can be able to put a regular framework in scientific practice where people try to have the input data and try to test their hypothesis against the observation, you expect to derive scientific knowledge in terms of general laws. So how you explain one pattern by using another in the real world. So that's the basic idea of deriving scientific understanding. But if we look back to the workflow we have regarding these two steps, it's very soon and clear that we can see that with the advancement of the data science and also the search of the machine learning based algorithms, we're in a situation that we encounter this reduced interpretability because the inputs of the model is just the images or image features, and the output of the model, your model, is a detected pattern. And at the end of the day, the interpretability is just reduced because you can only understand the pattern in terms of the image features, but which is still very powerful and useful in the community of the remote sensing. You could be able to still know what are the useful image features to extract these patterns. But it can be more interesting that we can explain the detected pattern by using some more understandable indicators regarding the patterns in the real world. So basically, this is what's going on in the current practice of detecting socioeconomic groups, especially the poor neighborhoods or people in deprived areas. And whereas the bottleneck is that there is a reduced interpretability in part of the workflow. This also partly explain the reason, or respond to the question that in these days, in many of the published journal articles, that people are discussing that why the increase of the knowledge is not really growing linearly along with the increase of the remote sensing data. So I think it's partly respond to that question, that kind of question. So to briefly summarize, I think the problem is that there's always a kind of ambition that people in remote sensing, they try to map directly the socioeconomic patterns from the image. And in order to interpret that, we have to jump outside of the scope of the remote sensing and try to do some geographic or geospatial-based analysis or statistical analysis outside of the scope of the remote sensing. So people are really, of course, reflecting on this kind of issue and are trying some alternative, try to bring more understandable or interpretable information regarding the poor neighborhoods. For example, 1 year ago, I think it's one of our students are trying to use more interpretable indicators to map a continuous pattern of level of poverty or level of deprivation over the entire city of Nairobi. And what he did is that he tried to combine all of these indicators, for example, like distance to health facilities, so accessibility to resources, and also population, building density. So these are more or less regarding the physical or living environments, and some other indicators regarding the air pollution and water resources. So by combining these indicators, he could be able to map out the pattern of socioeconomic status on the ground, while at the same time, of course, we can explain this map. So this map is created because some of the indicators are contribute more, etc. and etc. But in this case, we can clearly see that the role of remote sensing is not really related to this this simple operation. But if we look closer, what can be also see is that some of the indicators listed in the table are of course derivable from remote sensing. So people in remote sensing community are thinking about how about derive this information first, so that still we can highlight the strength of the remote sensing in mapping this kind of information. So what people are actually thinking about is that, is it possible that we can first derive more useful information? So there is a switch in the workflow. So this is how I summarize the ongoing practice, that people try to derive some more interpretable indicators from the remote sensing before mapping the socioeconomic status, so that the mapped status, the mapped outcome will be more interpretable in terms of the more interpretable indicators. In this sense, we're in a different workflow where we try to avoid directly mapping the target patterns that we're interested in, but try to map some intermediate indicators before we reach the final outcome. So in this way, and there are indeed quite a lot of people thinking about this workflow and say, okay, what are the indicators that we can use to still take advantage of the strength of the detection power of the remote sensing, so that we can derive some indicators that can be useful for interpret the socioeconomic patterns. So as I already talked about, that within this part of detection, there is a problem of interpretability. So once you map directly from images to some indicators or some patterns, there's always an issue that this mapped pattern can only be interpreted by this image features. So what we would like to have is that we more or less want to reduce or minimize the uninterpretable part. So uninterpretability, I don't know, this is not a really English word, but we try to minimize the pathway that we jump directly from the image to a mapped pattern, so that we can maximize the space, maximize the room or opportunity that we can derive more information to interpret the target map. So at the end of the day, that people will find that maybe it's beneficial for us to just stick to the most basic urban elements and try to start from these very basic elements to build the interpretation of the mapping outcome. So actually, this is quite beneficial because if you think about the nature of the remote sensing, that it only sees physical information from above. So why not just stick to this nature that try to extract the physical information alone and build something on top of that? So people are actually trying this, and this is not new, I would say, because trying to interpret the urban patterns or trying to understand the urbanization or its socioeconomic status in terms of these basic urban elements is naturally linked to the area in urban morphology, which has been there for over 100 years. I think the history of urban morphology is definitely over 100 years, that people try to use basic urban elements such as buildings and streets, open spaces, and also the green areas, something like that, to understand the evolution of the cities. This is, of course, very interpretable information, and it's also understandable in practical context in areas such as urban planning and design, because these basic elements are actually exactly the level of granularity or the elements the urban planners, practitioners are work with. So there is already quite some practice in remote sensing community that people try to start with this a little bit shifted workflow. So as I show you that here is a study from a few years ago from Hannes Taubenbook that they are already trying to see if they can differentiate socioeconomic groups by using building configuration, which means after detection of the building footprints, as I said, you almost always have to measure something about on top of it. And then they try to relate these measurements to the poverty or socioeconomic status in the city. So as you can see that in the workflow, you detect the buildings and then you can be able to make some measurements and try to relate this pattern to different types of neighborhoods in terms of their socioeconomic or demographic status. So this is one example that people follow this updated workflow, I would say. Here is another example that people from our group, and this is actually a study led by our host today, Steph, where Steph and Angela, and I think Angela is also in the audience, that they try to also take advantage of these basic elements extracted from the remote sensing image. So elements such as buildings and open space, vegetation, etc., and try to build the relationship and try to use this configuration of these basic urban elements to explain the variation or divergence within the poor community, within the poor neighborhoods. As you can see that given the socioeconomic status around the divergent socioeconomic status around these poor neighborhoods in Nairobi, and you can also see that how they are different from their built environments. So you can have more, quite a lot of enhanced interpretability within the variability of these neighborhoods. But of course, even we have this opportunity to start from another direction, try to map something intermediate information and to enhance the interpretability. There are still quite a lot of challenges along this workflow. For example, one of the challenges that, of course, you need information about basic urban elements regarding buildings, regarding streets, and here we're only looking at the buildings. So, for example, there are issues related to the updates of this kind of data sets. So building data set can be outdated very soon. If you are thinking about how quickly cities are growing in these developing countries, of course, you can apply machine learning based models to extract these basic urban elements, the buildings. We do encounter a lot of problems by mapping the buildings from this very densely informally built areas. You miss a lot of buildings, and also I think you would miss quite some buildings in this area with high rises. Preferably, of course, you would like to derive buildings by artificially or manually, but that will be really intense and time consuming. So different challenges and bottlenecks also for this kind of practice. There are also open data sets showing the problems in their data quality. This is the data set, open building data sets from Microsoft, I think, where they claim a very high accuracy in their building data, in their building footprint data sets. But as you can see that in a very densely informally built area, the extraction of the buildings are very poor. But very interestingly, that the accuracy of this map can be very high, because most of the accuracy are built upon a small metric, which is called the true positive. So which is basically measuring the intersection of detected pattern and the real pattern. But in the situation of very densely built neighborhoods, you can, of course, draw some random polygon. You can always intersect with the buildings. So this measurements doesn't really make a lot of sense in a situation like this. We also try to extract building by ourselves by using publicly accessible datasets. For example, we try to use Google Earth images to extract buildings, and the outcome is not really desirable. As you can see, well, this is too small. Again, my apologies. We miss a lot of building in these densely built areas. And there's a highlighted problem in this cropland. Also, that because we're trying to apply a machine learning model, which we train the model on certain area, where the model tried to recognize this little square with a certain material as building roofs. But in this area with croplands, you have this bare crops. So the bare crops are square shaped and also with this muddy appearance, which are falsely recognized by the model as building roofs. This is really quite a significant problem, but we just try to proceed anyway. So apart from the building extraction, as I showed in the workflow, is that you need to measure something on top of the buildings. There are many measurements you can derive in the three-dimensional environment in the city. For example, you can measure the size of the building, the parameter, adjacency, height, whatever. And you can also measure something regarding other urban elements. But here, again, we focus on buildings. So what are the actually useful measurements? It's really difficult to define. So again, I'm showing this study from Hannes to highlight the problem that it's how difficult it can be to define or identify useful measurements to differentiate socioeconomic groups. As you can see, even within the poor neighborhoods around the globe, so different types of poor neighborhoods around the globe, you can see that how variable the computed building configuration in terms of the density, in terms of the building size. As you can see, sometimes the building size can be very small in these poor neighborhoods in Africa, but the building size can be with a lot of variance in other continents. So there's no existing prior knowledge that which are the most useful measurements that we can use to better differentiate or to make them more discriminate in terms of the socioeconomic groups. So in terms of so thinking back about the problem of classification, you can see that if you have a lot of variance in the measurements in the measurement space or feature space. So here the feature space are formed by this building configuration measurements. You encounter the situation of very large intra-class variance. So within the class, there's a lot of variance across the class. So the inter-class variance is very small, which means there's a very small chance for you to differentiate the neighborhoods only based upon the building, the building configuration. So holding all of these challenges in mind, we proceed with our own study cases. Here I'm trying to show you some examples of how to explain the poverty or the poor neighborhoods in terms of the building footprint or building configuration. So in Nairobi, this is our study area, which covers roughly around, I think it's over 600,000 buildings are involved in this study area. And this 600,000 buildings are, well, based upon the extraction of our of our model, which is not really accurate, as you can see. So I think it's just a rough number. So Nairobi is a very diverse city. So it's highly diversified. You see different urban areas. It can be very nicely planned urban areas. It can be very poor or crowded urban areas. So is it possible to explain this pattern by using building configurations? So let's see, we proceed with the building extraction, of course, over the entire city, and the problem I just highlighted before, without proper prior knowledge regarding what are the measurements or metrics to be measured. We just proceed with measurements as many as possible. So we don't know what are the most useful measurements for this study area. So as you can see, there are measurements starting from the very basic ones regarding the size of the building, parameter of the building, compactness, and also there are also measurements regarding the plots. So the plots is an artificially derived unit around each of the buildings. So in the building dataset, basically we don't have other information apart from the building polygon, but we try to derive artificial plots so that we can compute also something like a coverage ratio. So over here, so how a building is occupying a small unit area around each of the building. And this artificially derived neighborhood is based upon tessellation. So it's a basic GIS operation. We computed the matrix, and one of the matrix, for example, I'm showing the as an example is the building orientation. So which measures how the buildings are organized in the neighborhood. So in any part of the area, you can see different colors. The lighter colors indicates that the buildings are more or less nicely organized. So they are more or less along a uniform orientation. The darker colors shows that the buildings are less organized in terms of a fixed orientation. Basically, you can of course relate this pattern directly to deprived areas, to the pattern of the poor neighborhoods, their socioeconomic status, and try to see if this satellite derived information can be useful to explain or predict the socioeconomic status. What can be more important is that before we relate one or few of the measurements to the poor neighborhoods, it's also possible for us to first classify the buildings based upon these measurements, so that we can have a automatically derived pattern first in terms of the building configuration, and try to compare this classified building patterns to the poverty, to deprivation, to other socioeconomic patterns. This is what we did, but classification also means that there is the issue that you have to choose the number of clusters manually. So this is the problem in unsupervised classification in many cases. So we can use different number of clusters, as you can see, and we try to relate this pattern to some of the identified poor neighborhood by local non-government organizations, so local participants according to their local knowledge. And then we try to see if the built environments, which in terms of the building configuration, how they could be used to explain the pattern in the poor neighborhoods, in the socioeconomic status in this case. So as we can see that very interestingly, that many of the poor neighborhoods are more or less dominated by a certain type of built environment, which is of course much more interesting than explain the socioeconomic status in terms of the image features. So in this case, we can see that certain building types are occupying the poor neighborhoods, but this kind of building types, similar building types, are also falling outside of these poor neighborhoods, which means other social groups, other socioeconomic groups are also occupying very similar living environments, which also highlights our current limitation. That's given the limited measurements that we have, there's potentially some space to improve, to derive more measurements, more meaningful measurements regarding building configuration to explain the divergence in social economic groups. So this is our example, and for more details, of course, you can plot each of the indicators for different clusters, for different building types. So as you can see that for different building types, as we see in the color in this previous map, and how the computed indicators are different in each of these clusters. So you can make more detailed interpretation. And I think this information can be very interesting for planners and designers, and for them to think about what kind of built environment is related to the socio-economic status in the city. Of course, that was only one of the study case. We're trying to generalize this kind of study in different places over multiple African cities. As you can see, there are quite a few more cities. Actually, most of all of these experiments are conducted over the entire city, but to visualize, I just show a subset of the study area. So the poor urban neighborhoods in these cities, well, actually, we don't know what will be if we generalize this kind of study to other continents. But in Africa, we can see that the poor neighborhoods are more or less highlighted by certain similar types of built environments in terms of this dark yellow and red. So I didn't superimpose the polygon as shown in the previous slides, but that's a general rationale of our practice. And of course, as I said, you can generalize this kind of study to other continents, try to explain the socioeconomic patterns, for example, the functionality of the city in terms of its function in commercial, residential, industry, something like that, to see if the satellites derived information regarding the building configuration can explain more about the city in different places, in different continents. Apart from this practice, we also try to look further into the future. So I'm already in the closing part. I think the time is fine. We try to see if we can derive more information about other meaningful metrics over different types of urban elements. For example, urban streets, apart from the buildings. We also try to make the entire workflow open and reproducible. So for example, here we try to open the workflow regarding the building extraction on Keiko, and this is just feel free to jump in and try to use that. And there are other notebook on GitHub. We try to open the workflow regarding how you derive meaningful measurements over the detected urban elements, the buildings from the satellites. So as you can see that these are all open notebooks that we would like to share with you. So I think that's pretty much about a very quick overview of the current ongoing practice in deriving information regarding the poor neighborhoods by using remote sensing images. I hope that makes sense. And here is I don't have a lot of things to conclude, but there are the most, I think the most interesting 2 points I would like to draw upon is that we need to keeping in our mind that what is the role of remote sensing for deriving scientific knowledge, given that the surge of data science and also the advancement of the sensors and many kinds of data that we could be able to acquire these days. So I think that's pretty much about my presentation, and now I'm open to questions and comments.